Hi, everyone, and welcome to this new session of the Vertica Unified 2022. My name is Badr, and I will present today the best practices for VerticaPy. We saw that VerticaPy is a layer at the top of Vertica, providing a lot of Python functionalities and pushing all the aggregations to Vertica. But when you're using this type of tools, you need to know how to use them, because we are providing a lot of optimization, and as we are pushing SQL statement to Vertica, we need to be sure that we are not hurting the system. So let's look at the agenda. So we will speak a bit about VerticaPy quickly, just 2 slides to explain again what it is and a little bit of the architecture. And then we will go through the different best practices. So in these best practices, we will see like why we should care about database optimization. We will look at why normalization. You know, a lot of people are normalizing the data without knowing exactly why. I will try to show with numbers why it is more performant to normalize the data. We will see also why it is important to select the right variables, and if you know why seeding or not seeding, for example, the randomness of some algorithms, and much more than this, because you have hundreds of ways of optimizing the computation in VerticaPy, and we will just see a few of those techniques. So first, VerticaPy. So VerticaPy, as I said, is just a layer at the top of Vertica. VerticaPy provides different objects, which we call like vData frame and vModel. And those objects connect to Vertica and then send the aggregation to Vertica. Vertica can push back the result. And then we can draw charts. We can do a lot of data preparation. We can evaluate, for example, a model, and much more, because we are using all the power of Vertica to do it. And it's very important to understand that VerticaPy is a layer at the top of Vertica, and it's not like another Python module that is loading in memory. It's really pushing back all the aggregation to Vertica. And it provides many functions to follow the entire data science lifecycle. But the big question you can ask yourself is, which function should I use and in which circumstances? Because depending on the use case, you will have to use different functions in order to have better performance or better accuracy. And it's important to really master this set of functionalities and to understand how they are working behind the scene. Let's move to the best practices, because now that I insisted on what's VerticaPy, we can now understand like how to optimize it. The first thing is, I'm always saying to customers and VerticaPy users that as VerticaPy is just a layer at the top of Vertica, the first thing you should do is to optimize the architecture at the database level. If you're looking at it, VerticaPy is a Python layer, like it's just the Python interface on the top of Vertica. But what's important in Vertica, like if you were speaking about optimization, it's really to work on projections and segmentations, because if you don't have the right projections, if your data is not equally distributed across the node, you will not use all the potential of your cluster. And as you are just sending SQL queries to Vertica, if this part is not optimized, VerticaPy will be slow. So VerticaPy relies on Vertica. And if you do not optimize your architecture at the database level, you cannot expect high performance. So the first advice I can give you is to master your database in order to optimize, like what you can optimize at the database level. But then, if you know if you're already optimized like your projections, your segmentation, then you have multiple tricks, multiple functionalities that you can use directly in VerticaPy. So to maximize the resources, you have multiple ways. Let's take the example of the describe function. So when you describe the statistics, you're sending one query to the system, like a summarization call of all your numerical columns. And then Vertica can compute all the aggregations, send back the result, and then VerticaPy can display this result. But why sending one query when you can still send multiple queries? And that's an idea, because just imagine here we are just using a data set of 7 or like 9 columns. But just imagine that you're using a data set of hundreds of columns, and then you are in an environment where you have high concurrency. A lot of users are sending queries to the system. You can hurt the system because your big query will take a lot of resources. So what I did in order to be a good neighbor, like you don't want, to hurt the system because some other are working in the same system as you, is to send multiple smaller query iteratively. So here I'm using, for example, 3 columns per block of query. And you can see that here, as I have 7 columns, it will split my work into 3 queries using 3 columns for 2 other queries and 1 column for the other one. And it's a way to not hurt the system and get the same result. And we will see after, in terms of performance, that it's still like pretty good to do this type of operation. After, there is something optimal on the number of columns you should choose for each query, and you can determine this number for your environment because it will depend on the resources and other factors. But still, here I'm dividing my work, and I'm just sending very light queries to the system to get my result. One other things we can do is sending multiple queries at the same time. In terms of resources, maybe we will use the same, I would say even sometimes less than the big query in terms of resources. It will really depend on the use case again. But what's cool about it is that I'm sending multiple smaller query at the same time, which means that Vertica, when it will not have enough resources to do it, it will put it in a stack, and then it will wait to get enough resources to run it. But at the same time, you're computing the other smaller one, so you're not really hurting the system like you can do it with the big query. And then, of course, Vertica will gather all the results, and then VerticaPy will display the result. You can see in the parameters that you have the number of columns you want to use for each block, and also the number of workers. But here it's a little bit different. These processes will just create a connection and send a query. Vertica will still have to manage all the parallelization of the query itself. So it's a little bit different because, as I said, they are just used in order to send the query and not to do computations. So what's interesting, I drew this graphic in order to show you the performance that you can win by using the different techniques. So if you're looking at the first point, like at the beginning of the graphic, it's the one to send one query, which runs with approximately 40 seconds. Then we can send multiple queries iteratively. For example, 2 queries iteratively will take a little bit less than 45 seconds. But if I'm sending 5 queries at the same time, you can see that first I'm sending lighter query to the system, so to digest, so it's easier to compute. And as I said, if it doesn't have enough resources, it will just put it in a stack. But in this environment, I just, I'm just using this cluster alone when I did the experiment. But still, you can see that you can reach 27 seconds. And I saw for some use cases, even better performance. So it can be a way to win performance without hurting the system too much compared to sending one very big query with thousands of aggregations at the same time. And still, if I want to use and send iteratively, I can, take maybe twice the time with one big query, sometimes only like 7% more time. But at the same time, as I said, when you're sending the query iteratively, you are not hurting the system at all. You are really sending smaller queries than the bigger one. So knowing this, you should find, like in your own system, which technique is suitable for you. Maybe like you have too many concurrent users and you don't want to send 20 queries at the same time. Maybe you want to send them iteratively. Or maybe you have enough resources and you want to win in performance, and then you will send them at the same time. Or maybe the query is small enough to just like send one query to the cluster. So having all these techniques, just understand the pros and cons, and then you can even optimize this thing on the VerticaPy side, which is basically amazing, really. And one other thing that you can also do, because when you compute aggregations, you will use these aggregations for multiple things. It can be for statistical tests. It can be for graphics. For example, when you draw a bar chart, you are computing some aggregation for a specific bar chart. And what can be interesting is to cache the information. So in VerticaPy, you have also a way to cache the aggregation directly in the system. So you can use this option and set it to true. You can see in the code. And then when you will compute the aggregation, first time I did not compute them. So Vertica will distribute the execution and send back the result. And second time, when I will try to compute it again, then the results are cached. So they are stored inside the data frame object. So I just have to display the result. It will be instantaneous. It's a way to not hurt the system, because just imagine someone computing again and again and again the same thing, whereas you have a lot of concurrent users in the same system. So it's really a way to not hurt the system and to be, like in this case, a very good neighbor. One thing you probably know about Vertica is that, like, when we speak about aggregations in general, we think about the most popular one: minimum, maximum, standard deviation, etc. But some of them, are not really built to scale, because if you're thinking about a median, it's really hard to divide the work of the cluster of the different nodes for a median. There are some techniques in order to have something approximate, and those techniques can scale. And here I'm showing you really an example on the different, let's say, aggregation. And what I'm saying is that if you don't need an exact value, because we are working with data sets and most of the time, approximation is enough. And if you don't need to have the exact values of the cardinalities of a column or to have the exact quantiles, use approximate quantiles. Use approximate cardinality. Just look for the quantiles. I'm just running here. It's a very simple environment. And I'm computing, let's say, 1,000 aggregations for 100K rows and 1,000 columns, sorry. And you can see that you will take 35.7 times less by computing approximate quantiles than computing the real one. So we are going from 54 minutes for exact quantiles to 1 minute 30 seconds. It's really huge. And you can imagine that in bigger environment with terabyte of data, the difference will be even larger. And, you know, if you're looking at the approximation and you're computing the average error rate of the approximation, you will see that we are in less than 0.1%, which in my sense is fair enough when you deal with like, let's say, big data use cases. Of course, if you need the exact one and the use case can only be solved with the exact one, choose the exact one. But whenever you can, just choose the approximate one. Same for cardinality. Just look at the difference. We are taking 125 times less by computing the approximate count distinct rather than the count distinct itself, which it took 30 minutes against 14 seconds. So huge difference. And again, you can see wider difference when you work with bigger tables. I will always give you the same advice, because this advice, I think you will hear it often, not coming only from my side. You have really to understand what you use. And some people are saying, like, you know, we computed this function and it took too much time and we don't know why. Vertica must be fast. Yeah, Vertica is scalable. Vertica is one of the most powerful columnar MPP database in the market. But if you're using very heavy computation, we will try to optimize it the best we can. But still there are some stuff that you cannot optimize easily. And understanding what you use means when you use a technique, try to see what it will do behind the scene, the mathematical knowledge you're using. Example, I'm using here Pearson and Spearman. And we can see that Spearman is taking, for this example, 21 times more than Pearson. Sometimes you will have exactly the same execution time because you're working with a very small data set, but with very heavy data set, you will see that this gap will become wider and wider. Because Pearson is easy to compute, it's just, you know, you're just computing basic aggregations behind the scene to do it, whereas Spearman needs to sort the data and you need to compute the rank of each individual variable, which can be really a pain for any database. And I'm not speaking about Kendall, because for this type of data set, Kendall will take even hours. And I did not take my time to wait hours for the different computations of Kendall, because Kendall is using typically a cross join of the entire data set, which can become really huge in case of big data. So understand what you're using. Sometimes you say, yeah, maybe like Spearman will be better because you want to get the monotonic correlation. But sometimes, for example, here, the linear correlation can be well enough if you want to check the linearity of your model. You don't need sometimes to check for monotonic relationship, even if it's more precise. And I can give many advices about understand what you use, but just show the one on correlations. But you can have many for machine learning. If you do not know what you're using in terms of machine learning, it can be a mess when you build model. You can just ask yourself why it's taking too much time or why it's not working. It really depends on this type of knowledge. Like, you must know what you're using. Like this, you can expect to wait a lot. You can expect to have good result with this data set, etc. You can have this basic data science knowledge. So one other advice is like to save your temporary relation. And it's one of the biggest advice I can give you, because if you're looking at this example, like I'm using the Expedia data set to do some sessionization and to build some user sessions, you can see that I'm doing a lot of operation. So I'm computing some sessions. Then I'm using analytical functions to compute the most occurrent hotel cluster in one session. So typically in this use case, we are trying to understand if in a specific session, the user will book or not. And we are computing many aggregations. But by doing all this operation, as I said, with virtual data frame, we are not saving this result in database. We are generating all the time the SQL query in order to compute the results. And it can become really, really expensive because just imagine that you're doing hundreds of operations. The SQL query will look like something like this. And here I just did a few of them. It can become wider and wider. And just imagine that each time you are querying this table, or each time you need to for example, build the model, you need to call this table. You can see it as a view, as a constantly updated view. And so you can understand that it can become really, really expensive. So in our example, which is not like a very big example, like 12 millions of rows, you can do even hundreds of millions. We are winning more than 100% of the view time by just building the table. In the example, we are doing machine learning. Basically, we are like taking our V data frame and then doing a cross-validation on the booking variable to see if a user will book or not. And we are using a 5-fold cross-validation. And we can see that, yeah, it's taking twice less by building the table, which is good, really is good for this use case, because we are using a very powerful cluster for few rows, like just some millions of rows. But the difference will become much wider when you will do more operations, and of course when you will increase the size of your data set. And that's one of the most simplest advices, and the one that is really working well, because like you will always win time by saving your relation. Of course, if it is a very simple data set with few rows, or if you did few operations, you don't need to do it. But when you reach a point where you did a lot of operation, a lot of transformation of your data, please save your temporary relation. Now that's a big question, because like a lot of people are normalizing the data without understanding why normalizing the data. Because in mathematics, yeah, I can, like theoretically, I can put my data the way it is, and then yeah, if it converges, I will get like I will always get my result. And plus that, if I do not normalize, I keep the range of my variables, so it's easier to understand in a way. But normalizing the data means that you will do less operation when doing, for example, when using some machine learning algorithm. So here I'm using the logistic regression, which like at each iteration, it's trying to find an optimal value. And here it is. It's like, because that in computer science, like 1 + 1 is equal to 2, but 1 + 1.0000, and you can put 100 of 0, 1 is also equal to 2, because we cannot save all the digits. We have to play with the space we have in order to save what we can. But now I'm coming to the point. Just imagine that you are doing the sum of numbers that are not scaling the same way. One that is very big, like, I don't know, 10 exponent 99, and one that is very small, like 1 exponent minus 99. You can understand that your machine will not be able to do the operation correctly. You will have a lot of bias in each addition. And here it is. When it iterates, some computation are reached by the bias, and then you are having a less and less precise result, which leads that you will increase the number of iterations to converge. So in order to converge with, like, let's say, the data that is not normalized, in these use cases, I took 56 iterations. By just normalizing the data, we are taking 14 iterations. It's a lot, because just imagine that, I don't know, just imagine that in a big data use case, each iteration can take 1 minute or 2 minutes. So we are dividing by 4 the number of iteration, and by 3.6 times the time needed to do the operation here. So it's really, really huge. So we are not normalizing the data really to make the model better, but most of the time we are normalizing the data in order to converge faster. So that's one of the advice I can give you in terms of machine learning. Now, there is another question which is related to seeding or not the randomness. And that's a very good question, because in a lot of countries, we have to be able to reproduce the result. We cannot use a model that cannot, that we cannot reproduce with the data we use. And when we do not seed the randomness, then we cannot reproduce this result, which can lead to sometimes legal consequences. I know that in some countries, they really have to reproduce the result, because they cannot say that this model is predicting the credit loan this way, and then that's it. Because if you cannot reproduce it, if the model can be changed, and we cannot track this change. And this is why they need to use seeds when building some models. But by seeding the randomness, you are killing the performances. Vertica, as I said, is a columnar MPP database, and it likes to not sort the data all the times and have a specific order in order to do the computation. Because by seeding the randomness, what we are doing is we are storing some kind of sequence of number in order to be able to take the data in the same order we did the last time. And it has a huge cost, because I cannot process the data the way I want and the way it comes in and out. So I need a specific order. And by seeding this randomness, you can see that for a very simple model, which took 21 seconds to run without the seed, it will take 12 minutes. So 35 times more. It's a lot. It's really huge. So this is why I advise to know what you use. So when you seed the randomness, you have to understand why you're seeding it, and you have to expect that you will not have amazing performances. So I really recommend you to never seed the randomness when you can. Do it, of course. But you see the differences with a very small data set. Just imagine with a very wild one. And just imagine with a data set of billions of rows, the difference will be even bigger. Or even if you change just a bit the parameters of a tree, you increase the depth, the difference will be much, much bigger. Then there is this point where a lot of data scientists are just throwing some variable in what they call a blender in order to find the correct model for the variables. So what I did here, I added a lot of bias in my table. So I added 300 random values. They will be always discarded, but it's just to give you an example on running a model with some bias and without bias. So with bias, you can see that we are taking twice more than without bias in this example. But here I'm taking a random forest again. And for random forest, most of the bias will be discarded because of the way the algorithm is working. But not only you are losing performance, you are losing also accuracy. Like I'm losing 1.2% of AUC there for the same data set. And I ran the experiment many times with different, sometimes like, you know, the random forest is taking a set of value, and sometimes we are only taking bias in these values. So it will have to do the split on bias, leading to bad prediction. Plus the fact that your algorithm will work on like much more data. So you will have to all the time work with all the data set, which can take spaces, and the model size will be, of course, bigger as well. So to select the right variables, there is a simple way in VerticaPy. You can use a stepwise, and you can see that all the bias will be discarded during this stepwise. Of course, stepwise is not perfection. Like, it's not the best technique ever to select variables. You have a lot of them, but to discard bias, it's one of the most powerful techniques, because if the variable is not used at all, then it will be automatically discarded by the stepwise. So just please select the right variables. You will win performance and you will win accuracy. So it's one good way to work in Vertica. And you can see also that the stepwise will give you some kind of features importance. So at the same time, it will bring you some information about the features that are important in your specific use case. So one other thing that is really important, but I guess you already know it if you're dealing with linear model. When we deal with linear model, most of the time we have to follow the Gauss Markov assumptions, and one of them is to avoid correlated predictors. So when you look, for example, at this churn data set, you can see that most of the features are correlated one to another. And that's very bad for linear model, because they are trying to converge, they are trying to give a weight to some of the coefficients. And in this case, just imagine that two coefficients are correlated one to another. Then the algorithm will not know to which coefficient it should give more values or less value. One way to deal with it is, of course, to use a PCA to uncorrelate the features. Know what you use, because a PCA will not have a meaning of the feature. So maybe I will not be able to use a PCA in this case, but here, just to show you, you're winning 2.5% accuracy with by just using uncorrelated predictor, and it can go like the difference can be much bigger in a lot of use cases. But when you cannot use a PCA, try to discard one of the two features that are correlated one to another in order to avoid wrong predictions. That's another advice, but it's a common one. And do not forget, like, to use, let's say, non-correlated features, and of course, correlated features to the response, which means that you can look at a correlation matrix between your response column, like the one you want to predict, and the predictors. Because if they have no linear relationship, they will never be used in a linear model. So you are adding more variables, and that was one of the best practices that I said before. Try to select the right variables. Another interesting story and another interesting best practice is like to convert any Python UDx to C++. We got a use case where we had to do some extreme gradient boosting deployment inside Vertica using user-defined functions, because they had some kind of specific structure of file that they wanted to deploy in Vertica. And at that time, we did not have PMML, for example, to import it. And now we have. And we wanted to use user-defined function. And we know that Python UDxs are much less performant than C++ UDxs, specifically when doing scoring. And we know it. So one idea can be to develop a Python UDx, see if the results are matching, and then trying to write the C++ code of this Python UDx. That can be an idea. But in all cases, when you're using low-level programming languages, most of the time you will have better result than a high level, of course, specifically in terms of performance. So here, really, when you can, just use C++ UDxs. One last advice, which is basic, it's like close your connections, because when you use VerticaPy, you are creating a connection to the system. But just imagine that you have multiple notebooks where you create different connections and different sessions. So you will probably face this error message, like that the new session are rejected due to the limit. For example, here I have 55 sessions that are active, so I cannot then do my work because I have a limit in the number of sessions. So just close your connection. Just use the close function, or the close method of your connector, or just use the close connection of VerticaPy in order to avoid these type of issues. So we're reaching the conclusion. So we saw many of the possible best practices in VerticaPy. You have others. I'm trying to write like some blogs around like all kind of best practices, but here are the one that are really easy to understand because they like when you understand bots caching or a bit on the machine learning assumptions, you can understand that it's better to not recompute twice the same thing. It's better to not use too many variables in your machine learning model. It's better to of course compute approximate aggregations rather than the exact one. So you have many things that you can do in order to totally optimize, and you can reach really high performances like by just achieving few of them. And do not forget to also close your connection when you're using VerticaPy, because maybe you will use multiple notebooks, and some of them can create useless connection, and then you will not be able to use also some optimization which create connection to do computations. For example, when we saw the example on maximizing the resources, and we were sending multiple queries at the same time, each of the query is using a connection. So if you don't have any connection available, it will raise directly an error to the system. So please, in this case, close your connection. Thank you very much for assisting to this session on best practices. I hope that you enjoyed the session and that you're ready now to get high performances on VerticaPy. Bye-bye.